let me ask you, and you actually just offered up information before class, which was good, because it's what I wanted to ask you anyway. I wanted to figure out where you guys were if you're taking digital image math right now. You're at the point of convolution filters. Now from this point you did histogram processing. What else?
Yeah, histogram processing was our last actual programming technique. We did Fourier transforms too, right?
Discrete Fourier transforms. Okay. Have you done any, so you haven't done any frequency domain filtering? Okay. We're going to do some of that in here today. So you'll have a leg up on there if I'm assuming you'll get that by the end of the quarter. That's awesome. All right. So who's, as far as backgrounds goes, who's done any image processing in the past? All right. And has anybody done things like using packages like NV or AirDOS to do land cover classification? Some have, some haven't. All right, so we're gonna go through that that sort of analysis. That's what I want to lead up to is the ability to take multispectral and hyperspectral data and start to understand what we're looking at in an automated fashion. And as sort of an introduction into that, I want to do just some of the basics of well, not the basics. I'll say more of the advances of image processing. Something that you probably will start to see near the end of this quarter, beginning of next quarter, if you might be taking the dip class also. And I also want to review some multivariate statistics. Now, I say review multivariate statistics. Who's had multivariate statistics? All right, good. That's okay. So the review won't be boring. Univariate statistics, everybody's had, right? You've done things like Z-tests and T-tests and understand, you had two populations and you were trying to figure out the mean was the same. You've done things like that, right? Okay, so it's called a Z-test, but as long as you know the concept. And probability distribution functions, you've seen those sorts of things. All right, so we'll build on top of that and move into a multivariate statistical understanding based on that. Now, that being said, if anybody's looking for a great elective to take as far as to fill out your degree requirements, there is a multivariate statistics class that's offered in the Center for Quality and Applied Statistics. It's actually called Multivariate Statistics for Imaging Science. So it is a course designed for you guys. All the data is multispectral and hyperspectral data and reflected spectrum, things like that. So it is specifically put in place for people who are interested in remote sensing, people who are interested in astronomical imaging, people who are interested in color science. Right? It's taught by a person over in the math department named Peter Byarsky and Emmett and Tolucci, who you'll have last quarter, right? He and Peter put that class together specifically for you folks. So if you are looking for a good elective, it's a terrific elective to take. All right, so let me start by trying to describe where we're gonna head. Now, I want to also start by saying the notes or the slides for a lot of the image processing stuff that we're going to be doing are not great. I'm going to probably go off of them quite a bit. There's some mistakes in them. There's some mistakes in the text too. I can go talk to John and get those fixed because some of the examples in there aren't correct. So we'll go back to the original papers to look at a lot of the stuff because I think it's better there anyway. All right, so the concept of image classification, where we want to finally wind up after we go through all this, is we want to take this remote sensing image that we've acquired, whether it's a hyperspectral scene where we have very detailed knowledge of the spectrum of all the pixels once we correct for the atmosphere. Whether it's multispectral, where we have a moderate resolution or a moderate understanding of what the reflecting signatures look like, or even if it's a single band, right? If we only have a single band detector or system, you know, can we achieve any sort of land cover classification when we just have gray line? That's a hard thing to do. Imagine seeing the world in black and white and trying to distinguish between things. Well, if you watch movies, right, older movies, you understand what's going on in the movie. They're in black and white. You know what you're looking at. So you, as human observers, can see in black and white and understand what you're seeing. Now, imagine that you're trying to do the same with an automated algorithm, right? You're trying to make the computer understand what it's seeing, but all it has is a black and white image. So let me ask you, when you, I wish I brought an old movie in today. You could have watched a little bit of it. You could have told me, you know, what was going on. Hey, that's a guy walking across the screen. He has a suit jacket on, a hat. He's probably going to a show, right? Because he's walking down the street and he's in New York and it looks like Broadway. And you just have all this understanding of things that are going on. And are you really, what are you looking at when you see all that? How are you making those decisions?
We have context and cultural awareness. Like we were talking about the first week of class.
Yeah, context, cultural awareness. It's exactly the way you do photo interpretation. All right? Now, if I was to try and train an algorithm, you know, an automated algorithm to do that same thing, well, now you're going to get into a realm of things which, you know, maybe you've looked at in the past. If you've gone through a computer science or an EE program, maybe you've taken an AI course at some point and you tried to do understanding, and you realize that this is a very tough thing to try and teach a machine to do. Things are getting better at doing it. It takes a lot of computing power typically. So we're going to take up baby steps, right? So if you go back and think of the photo interpretation cues that we had, context was one of them, right? One of the other ones, though, that was in there was texture, right? And for a while now, actually starting back, the paramount paper that we're going to look at is this paper right here. It's by Bob Haralick at the University of Washington at the time. It's from 1973, right? So we're going to go way back in time to when people started thinking about this. This is still the paper that everybody references when we're trying to do classification of objects in a scene based on their texture. Right? Nobody's done anything much better than this to this point. So that's why we're going to go back that far. But if you think about that, 1973, nobody saw 1973 here, right? Good, you missed disco, it was a great thing. But at that time, I mean, the concept of a computer was something that, I mean, I didn't think of. I was 10 at the time, right? And I never even thought of a computer. You know, I would see, you know, Star Trek just got off TV, right? You know, so I mean, the series just ended. They talked to this thing called a computer, and it answered back to them. So it was very science fiction to all of us at this point. But this guy, he was at the University of Washington. Who founded the computer science department at the University of Washington? Why does it exist? Well, it's this guy who started this small little company called Microsoft, right? So Paul Allen and Bill Gates pretty much established the entire computer engineering and electrical engineering department at the University of Washington, because that's where I'm going to go off topic here a little bit. If you're looking for, I heard some people say they have a little downtime. What are you going to do with that? If you want a really quick read, you know, just a book to read for enjoyment. I don't know if anybody's read the book by Malcolm Gladwell called Outliers. I mean, it's a terrific book, and it describes how the people who we think are the greatest people, you know, the greatest minds, the smartest people in the world, how they're not all that much different than anybody else, and but it was the situation that they were brought up in. It's the opportunities they had. It was their chance to get the 10,000 hours to do something, which takes you to become an expert. If you dedicate 10,000 hours to something, you'll be an expert. Okay? That's the simple message of this book. And Bill Gates lived near University of Washington at the time, and he had the opportunity to go there and steal time on their mainframe computer when he was 6, 7 years old, and nobody else just had that opportunity. So it could have been you, right? You could have been there. You could have stolen time on a computer. You could have got the 10,000 hours, and you could have founded Microsoft. It was just, you know, that sort of. Now I have no clue where I was going with this. I was talking about Haralick.
Yeah,
University of Washington. Okay, so 73 or so, they had computers. All right, there's where I was going. They had lots of computers at the University of Washington. It's one of the first places. The University of Michigan, University of Washington were the two universities in this country who had mainframe computers available to them. So they had some time to think about this. And if you look, it's awesome, right? I mean, this doesn't look different than a paper that you see now. You know, gee, that's equations maybe, but here they come. But you read through it, and all of a sudden you get here. That's their images, right? They printed images on paper, right? with this code called overstrike. So they were dot matrix printers that had to go back and forth a couple of times. And that's a remote sensing satellite image, believe it or not, right? This is mountains, and this is a grassland at the edge of the mountain, right? Hard to tell, but that's how you can kind of date this paper. But that's okay. It's still a visualization, but they were able to do this kind of stuff. It was before anybody else was able to. But then Haralick had the foresight to start to think, how do people understand when they look at things, what they're seeing? And his premise was that texture is going to be one of those key tools that people use. Okay? And if I show you, if I gave you a little paper towel roll, right, a toilet paper roll, take that and just start looking at the world through that. And if you start to look at things like a wall, right? If you look at the wall over here through a small, little aperture, right? If you stare at it long enough, you don't have the context any longer. You don't have the surround. But if you stared at that long enough, I bet you'd probably make a good guess after some time that it was probably painted drywall. Only because you've seen it so many times. Right? If you looked at a cinder block, and a cinder block kind of has that look about it. And after a little bit of time, you'd understand what you were seeing. A slab of asphalt on the ground. Looking at it, even through a small aperture with no context around it, you'd eventually realize what it was. I could probably fool you all day long by showing you other things that you would never guess because of the context. But in general, I think you'd probably do a pretty good job of understanding this. So, with no other information, what Haralick was proposing here was that we could do classification. We could assign pixels in the digital image to a particular material type or a particular land cover type based on just the texture. 1973 again, there was color film, there was return beam Vidicons, right, early video cameras, but that was the only source of color imagery at the time. And there were, just starting to come online some monochrome electro-optical type sensors, right? So it was very early on. So really there was no digital imagery at this point, short of something that you would take and you would go ahead and digitize like we talked about earlier. All right, so, but the nice part is that nothing's really changed except that now all of a sudden these things are much easier to do. Right, so let me go through and show you what he proposed at the time. And think about the monumental task that he actually proposes in this paper, and think about what all the other faculty and students at the University of Washington at this time, and everybody who read this paper thought of this person. because this is an insane thing to think about in 1973. The beautiful part now is it runs on any Mac or PC laptop in a matter of seconds, right? But the foresight that was here was quite shocking. All right, so how do you identify a texture? What is texture? In the case of a digital image, how would you say whether something was rough or smooth? Let's start with that.
Some kind of pattern?
Some kind of pattern showing up, right? If it's smooth, it'll tend to be a uniform gray level. If it's textured, it will tend to have some sort of localized contrast change, right? Because of light, right? I could light a very textured surface in a particular way that I could make it look like this, right? But if you have a source, like you have in this room, you're going to see small shadows in the cavities, and it'll appear to have a lot of contrast on a local basis. All right, so those small changes in digital count as a function of position, you need to come up with a way of characterizing that. Now, pattern's a whole different story too. You can use a really simple statistical measure, right? How do you measure variation? You take a population of data, you compute the standard deviation, right? If it was a bunch of changes from dark to bright, your standard deviation of the histogram of that area that you're looking at would tend to be high. If it's smooth, the standard deviation would tend to be low. All right, well that'll tell you something about the histogram. But it doesn't tell you anything about spatial patterns that might start to show up. Right? So, textures are more than just changes in brightness. Textures are patterns. You know, if you showed, pull up some pictures here. All right, so let's say we pull up a cornfield. What sort of texture do you see there? Well, you see a lot of changes from bright to dark, okay? Over even some small areas, right? If I try to make a moving window here, you have changes bright to dark, even in that small region. Now, if you look at a larger scale, what do you see?
Yeah, Greg said something.
Whoop.
You can see the vertical line.
Yes, it is. I wasn't going to point that out, but you sort of see some vertical structure, right? All right, so let's texture. That's where we're talking. So there's these vertical lines. There's that structure. If I look in a small neighborhood, though, do you see that structure? Right? It's only when you see it in this larger context. So texture is not only what happens in this small little, rectangle that you might make right. All right. That you might make right here. Right? It also depends on this rectangle that you might make right here. Okay? All I had to do was click on that one. Then we would have got through this a lot quicker. All right, so that's one sort of thing that you want to find. It's a pattern, right? It is a pattern. It's not just something that you can measure with a simple statistic. So you need something more than that simple statistic to do it. All right.
So how do you get permission to go as an
well, that's the beautiful part. You don't have to when you go to another country. You have to when you do it in the U.S. When you go to another country, you're just taking a risk. It's a really stupid thing. There, back to the paper. All right, so being able to characterize these patterns as opposed to just the statistical variations were what Haralick was going to try and go after. All right, so in order to do that, he came up with this new concept that's called a gray level co-occurrence matrix. Right? That's the name that it's evolved to. So gray level co-occurrence matrix. So what does that mean? It means it works on simple gray levels, so any band of a digital image. Co-occurrence means that he's looking for two digital counts that are in some pattern with relation to one another to occur simultaneously. So the co-occurrence. And they're defined by these equations right here, which is a really sort of nasty notation. This little pound sign means you're supposed to count things. So it's a histogram. Right? It's a histogram of when you look at position KL and MN in an image simultaneously, in a neighborhood that's defined by a dimension L sub y by L sub x, how often do two occurrences of digital counts occur? All right, so rather than try and understand this notation, because it's totally unimportant, let's just go look at an example and just show you what it is. I mean, it's so much easier to do this way. All right, so if this 4x4 area right here is a digital image, okay? It only has, in this case, 4 digital counts, 0, 1, 2, and 3. So just for simplicity, just to show you how this might happen. All right, what you're going to do is you're going to look at the pattern, you're going to look at the arrangement of digital counts in this neighborhood, and you're going to count co-occurrences of digital counts in that neighborhood. All right, so what does that mean? You're going to form this thing called a gray level co-occurrence matrix, and that's what's over here. So gray tone, 0, 1, 2, 3, 0, 1, 2, 3. The elements of that matrix are going to be the number of times that a 0 occurs next to a 0. The number of times a 0 occurs next to a 1. The number of times 0 occurs next to a 2, and so on. Right? This is how many times does a 1 occur next to a 0, a 1 next to a 1, and so on. This will turn out to be a symmetric matrix, right? Because the way we're going to count these things is going to be bidirectional. Right? So let's go through and do one. So let's say we're going to look at how many times a 0 occurs next to a 0 in the horizontal direction. Right? Because you can imagine we can go in all different directions here too. All right, so here a 0 next to a 0 occurs. So there's 1. Here's another one, 0 next to a 0. That's 2. No more going that way. But now you've got to scan in the inverse direction. So you go backwards, and whoo, there's another one. It's the same one that you already counted. You count it again, and there's a 4th. Right? So there's 4 times that a 0 occurs next to a 0 when you look in horizontal directions both ways.
And you don't wrap around, right?
You don't wrap around the edge. All right. So this matrix, gray level co-occurrence matrix right here, is the 0 degree co-occurrence matrix. All right. That means we're going to look in horizontal direction. So if you go back right here in this figure 1, 0 degrees means scanning across the image. 90 degrees up and down. 45 degrees on the positive diagonal, I guess, and 135 degrees on the negative diagonal. Okay. So we're going to form 4 matrices: horizontal, vertical, 0, 90, 135, 140, and 45. So that's going to be the gray level co-occurrence matrix. So let's just do another one. How about a 1? Let's see, a 0 next to a 1. Well, there's 1, there's 2. And if we scan backwards, there are none. Everybody see that? All right, so there's only 2 of those. All right. 0 next to a 2. Well, nothing there, nothing there. Here's 1. And if I go the other way, I don't see any. So there's one of those. Okay. So that's how you form this matrix. Right? Now for the vertical, you do the same thing. 0 next to a 0 in a vertical direction. Here's 1. Here's another. Here's a third. No more. Scan backwards. There's 1, there's 1, and there's 1. And so a total of 6. And you can go through and do these all day long. All right. So that's one parameter that you're going to look at. Now the gray level co-occurrence matrix itself actually has 4 parameters it's dependent on. Right, it's dependent on position, I and j. Right, so I and j, I'm sorry, not position, but gray level. So gray level I, gray level j. Right, so 0, 0, 0, 1, 0, 2, just what we're looking for. The direction, that's the last term here, 0 degrees, 45 degrees, 90 degrees, 135 degrees. Now, there's also a factor here called d. And a d is the distance that you are going to look in one direction or the other. All right, so what were we just doing? We were looking at co-occurrences of pixels immediately next to one another. So that d is 1. But you can specify d to be any number. So a 0 next to a 0, if d was 2, do we have any of those?
Horizontal direction, right?
No. We have 1, well, we have 2 in the vertical direction, right? 1 in the down and 1 in the up. So 0 here and then the 0 here. Okay. So what does that gain us? That gives us the ability to look at patterns that might be spread out over some distance. So let's go back to that cornfield example for a second. The rows were many pixels apart, right? Those lines, those vertical lines that you saw were many pixels apart. So a dark pixel next to a dark pixel in the horizontal direction, if those rows were running up and down in the image, you would get a lot of them if you picked the d to be the distance that those rows were apart from one another. You get a lot of dark next to dark pixel. So you get a really high count in the co-occurrence matrix for that particular location. And so that's how you would see that pattern. Now, if you looked in the 90-degree direction, I'm sorry. Yeah, if you look in the 90-degree direction, you wouldn't see those vertical rows, right? But you would see a lot of dark pixels immediately next to one another. So d equals 0, you would see a whole bunch of them because you had nice long linear lines of dark pixels running up and down. That make sense? Right, so you can see how the choice of parameters that you get here, you can really tune them to get the right parameters. All right, so now the big question, how do you tune these things? All right, well now here's the big question before the big question. That was a 4 gray level calculation. How many gray levels do you have in your sensors now? A lot more, right? 1024, 2048, 4096 is what we're having. I mean, most of our sensors are 12-bit that we use. How big is this matrix for a 12-bit image? It's 4096 squared, right? So you have 16 million co-occurrence values that you need to go and determine. And you could do that for a D of 1, a D of 2, a D of 3, right? You could do that for many levels of D, and you have to do it in 4 different directions, right? So this is why I was saying Haralick was a little out of his mind by proposing these things at this time, right? But you know, I'm sure as everybody did, everybody figured out we'd all have computers and robots would be vacuuming our houses and we'd all have flying cars by now, right? And you know, so we all have computers. That one came true.
Hey, the Roomba's true too.
The Roomba's here. That's right.
You don't really need to do every single iteration though, because when you think about, so like how high is your sensor? Do you really think there's going to be spatial patterns like a kilometer apart?
Absolutely.
So you can kind of tune it down.
You can tune it down. You can also say, do I really care if I get all 4,096 grade levels? Can I quantize the data by a factor of 16 and go down to 256 grade levels? Sure, you could do that kind of stuff.
And you only need half the data from the matrix.
Exactly. Well, no. I mean, if you went down from 4096 by 4096 to 256 by 256, and then you only have to compute half the matrix.
Yeah.
Right, because it's
Because
diagonal.
it's
Yep. Yeah, symmetric. Sorry. So definitely lots of things you could do to computation to make this tractable.
But you
All right.
also have to do it in 360 degrees too, right? Like this is assuming that patterns are in these four nice directions.
They are,
To rotate it.
and it's really all you can do, unfortunately, because you have this quantized space. I would love to do it in 360 degrees, and if there could be a Fourier domain equivalent of this, maybe you could start to think about doing that. But you could go horizontal, vertical, and plus 45 and 135 very easily, but how would you describe 37 degrees?
Yeah, you basically have to be doing like weird zero padding or something like that.
Exactly. So nobody is doing that at this point. They're just looking at patterns and hoping they line up in these particular directions.
Mm-hmm.
You know, this only works so well, right? But it does add a lot to your analysis. But in and of its own, it only works so well. So I think I told you earlier this quarter, my first project I ever did when I was working as a research scientist with the Deers Lab was to take a microdensitometer and scan film. Well, my second project I ever did with the Deers Lab was to implement this paper. And you know, it sounded great. I read the paper, it sounded wonderful. I started it running. I wrote the code, started running on a VAX 11780 mainframe that we had here on campus, and it was running, and it was running. And 2 weeks later, it still hadn't finished running on a 512 by 512 image from 256 ray levels. And you can imagine why, right? That's a lot of computation to be happening. And you know, every day, Schott would ask me, "Done yet? No. Done yet? No. Done yet? No. What are you doing?" I'm like, "Well, it's still running. This is a lot of computation." And you know, 2 weeks later, you know, it finally finished, and I actually got it right the first time, which was kind of cool. And then he wanted to run a whole bunch of images. Crazy. So then we started thinking, you know, can we quantize the image? Well, if I read this paper more closely, that suggestion was in here, right? So I probably should have done that. All right, so now what do you have? Well, for some neighborhood, now here's the other part. You're going to compute these matrices in some local neighborhood centered around a pixel. But now you got to move to the next pixel and do it all over again. And move to the next pixel and do it all over again. Right? So you're looking at some neighborhood, which you have to define the size of. Right? How big do you make it? Well, when we were looking at the cornfield, I said, well, if we looked at this small area, we don't really see the lines, but if we look at the larger area, you do see the lines. It's going to be very image dependent, how big you make those neighborhoods that you want to compute the grade level co-occurrence matrix in. But you're always going to center it at a pixel and come up with these four matrices for that pixel, and then move on to the next pixel and do it. But at this point, what do you have? Well, you have four grade level co-occurrence matrices, at least. You might do it at different d spacings. Right? So as many d spacings you have, you'll have that times four grade level co-occurrence matrices for each pixel. But what the heck do you do with that? How do you use this data? All right, now here's where it gets a little weird.
So that's how it took 2 weeks.
That's how it took weeks, yes. Absolutely. All right, so now what do? Well, that's the easy part. The next part is what you want is you want a number. You want a single number that you can put at that pixel location. Or maybe you want a vector of numbers, a series of numbers. But you want some scalars that you can put there that are essentially the equivalent of digital counts, right? Digital counts are brightness. Here what we'd like to have is a scalar that represented something about texture. Okay? So what Haralick is most famous for is, first of all, coming up with these grade level co-occurrence matrices, but then the next thing that he came up with, textural features extracted from gray tone spatial dependence matrices. That's what he called them first. Right? But textural features. Right? These are the scalars that are going to be computed based on the grade level co-occurrence matrices. Right? These are the single numbers that are going to come up and become digital counts, essentially, or augment the digital counts. So you can imagine, you might have an RGB sensor, and you might have, for every pixel, an RG and a B, but you might have a couple other values, other scalars that represent texture. And those values are dependent on these grade level co-occurrence matrices. Now, these textural features, to this day, are still called Haralick feature number 1, Haralick feature number 2, Haralick feature number 3, and so on. And he wrote 2 papers. He wrote this 1973 paper, and then he came out with another one in 1981. And in the 1973 paper, which is this one, you go back to the appendix, here's the texture features, gives some definitions, and then he defined 14 of them. 14 different features based on this grade level co-occurrence matrix. They had names like angular second moment, contrast, correlation, sum of squares or variance, inverse difference moment, sum average, sum variance, sum entropy, entropy, difference variance, difference entropy, information measures of correlation, and maximal correlation coefficient. All right, what the heck are these? Well, now is when you realize that this guy was really a statistician, right, and a computer scientist, and that's indeed what he was. And he just came up with this stuff for no reason. There's no physics here, all right? All right, there's no physics involved with these. In his 1981 paper, he came up with 18 additional features. So there's a total of 32 Haralick features that are available out of these papers. And you could probably come up with more if you wanted to. But let's take a look at a simple one, angular second moment. Right? What is that? Well, Pij. If we look back here, what's Pij? Pij is the ijth entry in the normalized gray tone spatial dependence matrix. All right, so essentially, that is your gray level co-occurrence matrix, an element in that gray level co-occurrence matrix, normalized by the total number of elements in your neighborhood. So just like you converted a histogram to a PDF by dividing by n, you're doing the same thing here. Right? You have a neighborhood that you're looking over. So let's say the neighborhood around the pixel that we're looking at is 100 by 100. R would be 10,000. So it's just normalizing the probability. Because that's all this is. It's a histogram of gray level co-occurrences. So it's just a normalized histogram or a probability density function. All right, so the ijth entry. All right, so what is angular second moment? Well, it's the squared ijth entry summed up. All right, so take your gray level co-occurrence matrix, square all the terms, add them up. All right, so think about that for a sec. If I have a smooth, perfectly smooth area like this, and this is a digital count of 92 in your image, and you have no other digital counts in this neighborhood that you're looking at, centered around this pixel. There's a whole bunch of 92s next to 92s, but there's nothing else next to anything else. Right? So you're going to have one entry in that 250, if it's an 8-bit image, 256 by 256 gray level co-occurrence matrix. Right? You're going to have one entry in there. And it's going to be all the times in 92 occurred next to itself. So in a 100 by 100 area, figure that out. Right? There's going to be 99 of them in each row, times 100 times 100, and then backwards. So 99 hundreds, it's almost 20,000. Right? That you'll have in one cell. So you're going to F1 is going to be 20,000 squared, plus a whole bunch of 0 squares for all the other elements that are 0 in the gray level co-occurrence matrix. Right now, if you had let's say you had random noise, right, with counts between 0 and 256. What would your gray level co-occurrence matrix look like if you were looking in a horizontal direction and you were counting how many times, a 0 occurred next to 1, a 0 occurred next to 2, and so on. Noise probably should come out to be almost the same in every cell. Okay, so if if it's almost the same in every cell, and you square those values and add them up, that number's going to actually tend to be small or large. Remember, you normalize them. So you have numbers less than 1. You square them, they get smaller. If they're small to begin with, because the energy is sort of spread out all over the array, this number is going to tend to be very small. In our previous case, where we had a 1 after we normalized it, this F1 is going to come out to be 1, so it's going to be very large. Okay? So a smooth area is going to tend to be very large. Very busy area is going to tend to be smaller or darker. All right, so now imagine you could form an image out of that. And it's going to be at every pixel location where it's bright, it means it's a relatively uniform area. Where it's dark means it's a very busy area in the neighborhood around it. So you're starting to look at the texture in the neighborhood around it and quantifying it that way. All right, so this one I can probably convince myself I might understand what it's doing. The rest of them aren't all that clear. All right, you know, let's just pick entropy. All right, you'll get to entropy next quarter, but you may have seen this in the past if you did any sort of signal processing. But entropy or it's also referred to as information.
I've seen it with
Okay. All right. So what's going to happen here? Well, this is the probability times log of the probability. In a uniform histogram, right, a uniformly distributed histogram, we have essentially the same probabilities in all cells. You have a lot of information in your scene. Where you have a narrow histogram, or you know, perhaps all your probabilities in one cell, you have very little information in your scene. Right? In fact, if you only do have information in one cell of your histogram, this actually comes out to be 0. So again, this one is going to be what? If you have a very uniformly distributed histogram, this is going to be bright. And if you have a single bin filled, like you would from an area that looks like this, it's very smooth, this is going to be dark, which is the opposite of what angular second moment was. All right, but my question to you is, do they provide any more information? Right, they're probably just perfectly negatively correlated with one another. Right, one's dark where the other one's bright. So the question is, do you need both of those features? Because you have redundant data. So there's 32 of these things out there. And in any implementation that I've ever seen of these, I've never seen more than 8 actually implemented in a commercial remote sensing analysis package. And the 8 that folks implement, I would say on average, should be the ones that aren't correlated with one another all that much, so they provide additional information. Right? But I don't know that that's always true. So let's take a look at what these look like. So if you haven't downloaded Envy, this is a free download that you guys can have. We have a license. Oh, you probably. Well, you will for the next lab. You're going to need to download. But let's just start that up for a second and see if we can run this real quick. Great. Let's see. Okay, so here's a Landsat thematic mapper image. Bigger. This one just comes with Envy. All right, so what does it look like we have there? It looks like we have some mountains, small town, maybe a highway that runs through there. little bit of snow up on top, but we have some nice uniform bright areas. We have some fairly uniform mid-level brightness areas, have some rough terrain over here. So there's a lot of texture here, so this might be good to try. All right, so if we go under, where is it? Where is it? Texture, there it is. All right, so co-occurrence measures. So you pick your input image, and let's see. Let's go ahead and just choose one of the bands. What did I show? 3, 2, and 1 here. Let's pick band 3. Okay, so we're just going to work on one of the bands and keep the textures, and work on the full scene. And okay, so here's the textures. There's mean, variance, homogeneity, contrast, dissimilarity, entropy, second moment, and correlation. Right? If we go back and we look at the paper, move that over here for a sec. What do we got? We got entropy. Homogeneity was not in this one. We have contrast. We have second moment. Correlation. Variance. So variance somewhere. Some variance. 4. We have 4 is variance. Right. So we have. These are the Haralick features. Processing window. This is how big of a neighborhood do we want to live in. All right, so 3 by 3. So that's a small neighborhood around each pixel. Co-occurrence shift. That's your D in the X and Y direction. Okay. Grayscale quantization. Do you want to do all 256 gray levels or smaller? Notice they don't let you do 256. That would take a while. Wait, I guess there's none. Yeah, so let's do 64. We'll let run none run for a second. All right, let's put our output in memory. All right, that's a fairly small processing window. Let's up that a little bit. 15 by 15. All right, so what does that mean? That means we're going to compute the low-level co-occurrence matrix with 115 squared. 225. Yeah. All right, so 225 possible elements, and we're going to use a D of 1 for this particular thing, and we're going to compute all 8 of the features. So let's let that go.
So when you do a 15 by 15, does that mean you're taking your original image and then subsetting it into 15 by 15 chunks? And
No, it means you're going to look at every pixel and look at a 15 by 15 neighborhood around it. So it's not tiles, but it is a 15 by 15 tile, but centered in every location.
But then what do you do when you're at the edges and you don't have a complete zero padded, or?
Yeah, well that's always the question in image processing. What do you do at the edges? You could zero pad. You could just start in that far and not compute out to that location. You could wrap the image around, which makes absolutely no sense. It's a choice at that point. A lot of times you don't want to lose the pixels at the edge, but you know you got to make that choice. All right, so that happened pretty quick. That was 2 weeks of my life in 1986, right? And that just happens that quick now. All right, so let's take a look. So what do we have? Band 3. So let's put band 3 on. Reference here. So there's band 3. And new display. And let's look at each of these. All right. So now, what are we looking at here? This is the mean of the gray level occurrence rate. Now notice, you see the black all around it? They just didn't go to the edges. All right, so essentially, that's not a texture measure. Right? That's the mean. It's a 15 by 15 blurring curve. That's been run over the image. So if you notice, mean wasn't out here as one of the options. So, but they did put that in as a texture. All right, so variance. Let's do that. All right, so where you had areas that you went from very bright to very dark, you have bright responses that come back. Where your gray levels are fairly uniform in a 15 by 15 neighborhood, you get dark responses. Around these little areas here where there's buildings that have contrast in the background, you can see they pop up. You can see the 15 by 15 window size here also. Okay. And along this ridge, you can see it has a bright response. But in the bright area itself, it's still low variance, so you can see it's dark again. Right? So what have you done here? Well, you've added a little bit of information to this. If this is all you had, you may not have been able to do a good job at classification. But over here, where you have these dark and bright edges, well, that's little gullies in the mountainside, and illumination's giving us some texture there. Well, that all shows up as a fairly bright area, so now you have additional information. Not only do you have this dark and bright area, but if you look at this bright area and you look at this bright area, they have the same digital count. If you were just trying to classify based on digital count, you would never do a good job here. You couldn't say that this gray and this gray, which are exactly the same, were different. But they're not the same once you add this texture measure. So now you have one more piece of information that's trying to distinguish between this gray level and that gray level.
Do they filter things twice to get rid of, like, I don't know a word for it, but like on the mountains, you don't really care about that, you know, it's just in the shadow. So if you were in the sewer again and did another contrast, it would probably make all of that dark, right? And then it would make those things in the middle with the town probably even brighter.
Well, but you know, go back to the mean for a second. You still have the bright and dark variations here. You know, shadows are always tough, right? Because you know this is grass on the side of a mountain in the shadow, and this is grass on the side of a mountain in the sunlight. Statistically, those are two different things from one another. Contextually, they're not, right? There are classification methods that try to take into account really just color, whether it's bright color or dark color, and if it's the same color, they call it the same. But most of the traditional classifiers will make those two separate manual methods, unfortunately. Well, I'll show you one then.
What's the rule of thumb for if you're actually looking for something like a car? Do you want to get it so that like the car is 1 pixel in the middle of 9, or like what's the best way to do that? Is there a best way to do that? So I'm thinking like if you were trying to find a car in this scene.
Okay, so let's say there was a car driving down one of the streets here.
So you definitely pick your window based on the size of the thing that you're looking for, right? Would you pick your window to be like 9 times the size of the thing you're looking for? So you had a neighborhood, you know, around it, or because it would get lost if it was too big.
Right. So if the neighborhood's too large, that this neighborhood that you're defining the texture over is too large, then that's only going to be one small variation in a very large neighborhood. The 3 by 3 that they have as a default is there because they're assuming that you want to find something around a single pixel. So you look at the 8 members around it. If the car takes up 3 by 3 pixels, then multiplying by 3, so making a 9 by 9 search neighborhood, is probably a good rule of thumb to start with. A car's not square, so a rectangular window might be actually a little bit smarter, but that's going to change depending on the orientation of the car. So the answer is, always make it a little bit bigger than your target, but there's no, I don't have a solid, you should always make it 3 times bigger, 6 times bigger. A lot of times it's going to be a lot of experimentation to try to figure that out. If you're trying to pick out of a car out of a large area like this, there's much better approaches to it than using a church classifier like this. Something like an anomaly detector would be the better way to approach it. So this is just one tool you're going to have. Don't try and use it on everything.
Okay.
All right, so let's look at a couple others just for the heck of it here. Homogeneity. Who's that? What do you see going on? This area right here, fairly uniform gray level, shows up pretty bright. Okay, this area in here, all the same gray level, shows up pretty bright. Mountainside over here, not as uniform, not as bright. Over here we have lots of stuff going on, contrast-wise, tends to be a little bit darker. So homogeneity, is kind of just like the word says, how homogeneous is the area. Contrast. Looks very similar to variance, doesn't it? Doesn't change on it. So those two features are pretty highly correlated. Entropy. That just says that the histogram is spread out, you're going to get a wide response. And if you look in most of these areas, in 15 by 15 neighborhoods, except in the most uniform areas, the histograms aren't going to be very narrow. Angular second moment. Remember we said very uniform area is going to be very bright? Most uniform area, very bright. Most uniform area over here, very bright. All right, so there's no physics here. It's really just trying to come up with some measure, some physical measure texture, because how do I say to a computer, I'm looking for rows, corn rows, right? I mean, again, that was a context, that was a cultural understanding of how people plant corn that made you be able to figure out what that field was very quickly. Still hard to do those kind of things. Okay, so those are Haralick's texture features. Right. What we're going to do with these, since they're one of the keys in being able to understand what you're looking at in a monochrome scene, you can only imagine if you have multispectral data or hyperspectral data, if you can add this on top of that, well, you should be able to even do a better job at land cover classification. Right? If you have color and texture, now all of a sudden it becomes a little easier to see things. All right. So hopefully that made sense. You know, like I said, in the text, there's definitely some typos in the text when Schott was covering this stuff. So I would just refer yourself back to the paper here for the best understanding. All right, you want to take a little bit of break, and then we'll come back and we'll take a look at a totally different topic. All right, start it over. All right, so the next topic I want to talk about isn't really, again, covered all that well in the book, and it's covered decently in some of the traditional image processing books, and it seems to be something that we tend to skip over a lot in other classes. So I want to show it here because I think it's very important for you guys to understand, and that is the concept of image restoration. Now let me ask you, in optics or in digital image math at this point, you said you've done a little bit of Fourier as so far as you've done the discrete Fourier transform, but you haven't done filtering using the frequency domain yet. Have you done anything in optics as far as image restoration goes? Okay, all right, so this is definitely worth going over. All right, so I have some notes that are probably good. I use them in my undergrad, Div 1, Div 2, yeah, Div 2 class. All right, so if you want to grab those, you can always just go to my site and go into Div 2, same username and password gets in there. There's a set of slides that I use in that class. Should come up. And somewhere around the middle, here we go. It's filtering or image restoration. All right, so let me start just by introducing the model here. All right, so you just started doing convolution. Hopefully this will work. So if I have an image, let's call it.
You're not ready.
I'm not ready. F of xy. Right, that's my image. if I wanted to model what would happen when I would go through an optical system and how that optical system might degrade my signal, right? I could do that using a convolution, right? And I might convolve that with what we call traditionally h of xy, right? Which is usually referred to that's normally referred to as a transfer function. Okay. The transfer function is typically the convolution kernel that would produce the same optical effect that a lens would have to blur your signal. So in other words, well, let me ask you, hopefully you've seen this by this point. If I take a delta function, a perfect point, and I pass it through an optical system, it's going to be blurred. Right? The distribution of energy that comes out on the other end is called the point spread function. Right? So h of xy is the point spread function for your system, or the transfer function. All right, now that's going to give you over here.
So the difference between point spread function and the transfer function is the domain in which they are?
Yeah, isn't the point spread function in the frequency domain?
I thought that it was the other way around.
No, point spread function's in the spatial domain.
And transfer function is in the frequency domain.
Sure. I don't know the answer actually. I always just thought transfer function was a more generic term, and point spread function made it very specific to optics.
I think Roger says impulse response for lowercase h and then transfer function for capital H.
Okay, well, you can imagine if you have an electrical signal, you could have a transfer function that's going to filter that. Right?
But that's usually in Laplace, or so it's always in the frequency domain.
We have a
Frequency. Yep. Yeah, optical transfer function, modulation transfer function, spatial domain and frequency domain. Absolutely. Okay. So now that I can't write any longer, let me try. So let's bring this into the frequency domain. We have G of uv equals f of uv, and you know the convolution theorem, right? That convolution in spatial domain is multiplication of frequency domain. Right, I'm going to stop drawing after this, I promise. All right, so if we can get to that point, then my question to you is, what I'd like to always have is my undegraded image, right? What the image looked like before it was degraded by my optical system. Now, if f of xy, if I call that my original image, or my scene, right, goes through my optical system, gets degraded by h of xy through convolution, I get g of xy. If I wanted to go ahead and do a deconvolution, essentially, I could bring it into the frequency domain. I could take g of uv and divide it by h of uv, and I'd get back f of uv. Through the inverse Fourier transform, I should get back f of xy, my undegraded signal. All right, now that's called direct inverse filtering. So the simplest approach to doing restoration is what's called direct inverse filtering. Now, there's a problem here. One's a simple computational problem. You're dividing by h of uv, so you got to make sure h of uv is non-zero at all locations. And actually, if you think about it for a sec, what does your typical point spread function for an optical system look like? Is it a big old fat Gaussian, or is it a fairly thin Gaussian? Hopefully it's a fairly thin Gaussian. So when you take a Fourier transform of that, it should become a... What's that? Wider Gaussian, right? If it was a delta function, which is what you love your point spread function to be, then it would be just a uniform constant function at the mean. All right, so this tends to be a little problematic at the highest frequencies, right? Because it is a big fat Gaussian that comes back, but it does go down to values close to 0 out at the extremes. So when you divide by this, you do get some instability at those highest frequencies. So if you start to get instability at your high frequencies, what happens to your reconstructed image? If I don't get my high frequencies just right, when I reconstruct the Fourier series, if I add together all my sine waves and I don't get the highest frequency ones just right, what starts to happen at edges?
It's blurry.
You start to get some ringing at the edges, and if I overall in the 2D spatial domain, if I don't get all those high frequencies just right, I actually create noise. Right? So what did I try to do here? I tried to get rid of the blur, and I might have done that, but then I introduced a whole bunch of noise because of mathematical instability. All right, so direct inverse filtering, while on paper looks great, and for examples that you might do in class will work perfect every time, when you try to implement it in the real world, it falls apart very quickly. And it also ignores one very critical thing, and that is that my signal that I usually have, that I record, usually has some noise in it, right? And there's no noise in this equation, right? So if I go back to this equation right here, I actually do have to add at each location some noise, n of xy. And you do the same thing in the frequency domain by adding n of uv. Okay. So I need to account, or I need to come up with a methodology to do that. Now, a simple ratio, or dividing by that Fourier transform of the point spread function in this particular case is going to take care of that. Right, because if I look at it, my actual signal in the frequency domain would be something along the lines of my original Fourier transform of my original image times the Fourier transform of the point spread function plus my noise divided by h of uv. Well, what does that leave me? It leaves me this. All right, and in order to get back to my original function here, I have to know my noise, and that's not always easy to do. But we can make some approximations to it. How would you approximate the noise?
By looking at something dark or bright or whatever.
Look at something dark, right? And whatever signal you have on top of that area should be noise. Put the lens cap on if you have that opportunity. And the image that you record should be the noise, as long as it's independent of your signal. If it's dependent on your signal, that won't work. So if you have correlated noise, that sort of an approach won't work. All right, let's assume we have some uncorrelated noise. All right, so in order to solve this problem, we're going to use the Wiener filter approach, which is a minimum mean squared error approach to the problem. Now there's a long derivation. If you go back to the original paper on this, the entire paper is a derivation. This is not a derivation I'd ever ask you to do on a test. Okay. Please write that down. do not try to figure this one out. Maybe you'll do that at the end of dinner. But what we're trying to do here is trying to minimize the error between our original image and our reconstructed or our restored version of that. So just trying to minimize the expected value of that square difference. All right. What comes out in the end is this, right? F of uv, the reconstructed image, right, is my Fourier transform of my recorded image G. So remember what G was. G was the blurred image. Okay. Times this filter over here. All right, what do we have in here? Well, we have the complex conjugate of the degradation function, right, the Fourier transform of the point spread function. And we have it here, we have it here. What's S of F? S of F is the undegraded image power spectrum. So it's the squared magnitude of the Fourier transform of the original image. that should be a little problematic. Right? If I have the Fourier transform of the undegraded virtual image, why am I doing any of this? Right, so keep that in the back of your mind for a second. All right, and then this term over here is the noise power spectrum for that particular system. So the noise power spectrum. All right, so I could probably get a good estimate of the noise power spectrum. All right, so let's do some rearranging of terms here. And this last term here is usually how the Wiener filter is written. Right? It's kind of nice because if you think about this, let's just look at it mathematically first off. If I have no noise, this term becomes 0. I have no noise in my system. Then these two terms, since they're the same, become 1. This fraction becomes 1. So what am I left with?
Our original inverse filter.
That's the direct inverse filter. So in the absence of noise, the Wiener filter reduces to the direct inverse filter. That's a good result. All right, now, what does the rest of this look like? Well, over here, I have my degradation function. All right, well, I can measure my degradation function. I could take my optical system into the lab, present it with a point source, measure the point spread function. I have it. Okay? That's all great to say, but then you strap your system on top of a rocket and launch it into space, and it vibrates the optics, and everything else goes on, and you no longer have that. All right? So you could do some really tricky things, and at one point I was asked to come up with a degradation function for Landsat. Right? John had this crazy idea that we needed to do some, with 30 meter pixels, we needed to unblur it sometime. And that made sense. You always want to try to do the best you can. And we figured, okay, how can you do that from space? I have a system in space, and I want to come up with the optical degradation function of that system. What do I gotta look at?
Just like on board, like an onboard black body or something like that.
Well,
Noise on board.
but remember, what do you want to? You want to look at something like a point source. You want to look at a delta function. And you want to see what happens to it. What's that?
Look at a star or a sun?
Look at a star, but that would imply that I can point it towards a star. And I couldn't do that. Stars would be great. So I kind of laughed because when I was out in San Francisco last week, I drove across the Bay Bridge to go over to Oakland, and that's what I actually used. San Francisco Bay, nice uniform background, Bay Bridge, perfect line. It was less than 30 meters wide, and as I'm driving across, I'm going like this. I'm like, man, it is less than 30 meters, right? And it was a perfect line source. So I had a line spread function that I could measure directly from space. And it was, works perfect. And that's, that's the way it'll do onboard characterization of this function right here, h of uv. You use that line spread function, take the derivative, you get the edge spread function, come up with the point spread function for your system, if you assume it's rotational symmetric. All right, so you can measure that, even on orbit. You can come up with the noise power spectrum, or at least a good estimate of it, all right, by doing a dark image, right, looking at a dark area or closing a shutter if you can. All right, so the only thing you're left not knowing is this power spectrum for the original image. Okay, so the way that this is where the paper ends too. This is the solution. To get back, you need to know this, which is what you're trying to get. Sort of leaves you a little unsatisfied. But the practical approach to doing this is what is your best estimate that you can come up with for this, for the power spectrum of the original image? Best estimate. Don't think too hard about this.
Just G of UV.
What's that?
G of UV.
G of UV. All right? Let's assume that our degraded image is the best estimate that we have of the original. And it is, right? That's what we recorded. Okay, so what you tend to do with Wiener filtering is you put in here rather than the power spectrum of the original image, put it in the power spectrum of your image. Filter it. It gets a little sharper. Then you do it again. You put in G hat, the power spectrum of G hat of UV, and do it again. And you continue to do it. You do this filter in an iterative fashion, and that's called the Wiener-Hellstrom filter, H-E-L-S-T-R-O-M. The iterative approach was added on later. And after 2, 3, 4 iterations, you can get very close to your original image, even in the presence of noise. And it doesn't suffer as much because of all the other terms that are in here from that division by zero problem that we had before Jaeger. So the iterative Wiener-Hellstrom filter, a very, very easy approach. Just implement this equation right here and make an estimate for the power spectrum of the image with the power spectrum of the graded image, and iterate each time replacing that power spectrum with your latest estimate. And eventually you'll get very close to that original answer. The undergrad class, I actually asked them to go out, take a camera, and do this, and measure the point spread function of the camera and come through and do Wiener-Hellstrom filtering. So, and the class was traditionally in the winter, so they'd have to go outside and find the point source. So I always suggested a headlight of a car very far away. Right? It would be a good point source. So one day, students came into class and they told me a story of how they almost got arrested the previous evening because of this project. I was like, huh, all right, well, tell me the story. So they were out on this road, East River Road, just off to the west of campus here, and it was snowing. It's winter, it was snowing. Well, most winters it snows here. And they pulled off to the side of the road on the left-hand side because the cars were coming towards them on the left-hand side. So they got out their tripod. So they were driving down the road, pulled across the road, and pulled off on the left-hand side. Right? It was cold, so they left the car running. It was night, so they left their headlights on. And they set up their tripod, they started taking pictures. Well, if you're in a snowstorm and you're driving down the street and you see two headlights, where are you going to steer?
Towards the house.
To the right side of those, which is off the road. So the car goes off the road into a ditch. And the students were like, oh, you know, totally thing. So the cops show up, the cops say, what are you doing? Oh, we're trying to measure the point spread function of our optical system. So the police looked at it and said, okay, you pulled off on the side of the road, you left your headlights, where's, and so they finally realized, oh yeah, that was probably a really dumb idea. I did get a phone call the next day. They let him go, but I did get a phone call from the Monroe County Sheriff saying this probably wasn't a good idea to do in the middle of snowstorms. So I said, I didn't tell them to do it in the middle of a snowstorm. But, you know, they survived. Nobody went to jail. And the other car, nobody was hurt, at least just the car. All right, so I'm not going to ask you to go out and do this as a project this evening. But it's not snowing, so you might have fun about it. But it is kind of neat. If you have a camera and you want to try this, just shoot something that's a point source. A laser pointer works really good most of the time, as long as you don't get it right on the wrong Bayer filter, and then you don't see it. But it will tend to work very well, and you can back this out and remove the noise and sharpen your image really quite well. So nice little experiment to try to get you. All right, so in order to come up with the best possible image we can before we start to do classification, right, to get our edges as sharp as possible, if we could remove that blur, and that's something you want to do in general all the time, you want to make your image as sharp as possible. This is really a physics-based method of doing it. It's not just going off and running a Laplacian filter over your image to make it look sharper. There's actual physical information about the optical system here that you want to use to restore it as best as possible. So probably in the next couple of days in DIM, you'll probably learn about Laplacian filters, sharpening filters, unsharp masking, different techniques to just blindly sharpen images. Right? You've probably done that in Photoshop or whatever image editing program that you do. In fact, your camera probably does it automatically when you take a picture. Most cameras run a sharpening filter. But you tend not to want to do that because, well, you're actually changing your data, and if you want to sharpen your image, you certainly want to do it in a way that you have a good physics-based understanding of why you're doing what you're doing. So this is essentially a sharpening filter. What's right here in the parentheses is your sharpening filter and frequency domain. Right? You could take the inverse Fourier transform of that, and it would be a convolution curve that you can apply as a sharpening curve. And that's sort of a neat exercise to do. If you can figure one of these out, do the inverse Fourier transform, take a look at it, and it's probably going to look very similar to what you'll see in BIM in the next couple of classes. All right. Questions? All right, so next time what we'll do is we'll go over some multivariate stats, just as a review, and then we'll hit classification, how we do multispectral classification. And probably next time we'll introduce the lab, because the next lab will be multispectral classification. So do a little review of your statistics if you haven't done statistics in a while. Look up a z-score. Kim?
I think I know what it is.
All right. All right. Know what a z-score is and know what variance is, and we'll be on our way. Just those two simple concepts.